Thank you. Okay, so my name is Cody, and I'll tell you about internal proof of star normalization. This is work in progress, which is to say it's not finished yet, and someday it might be. So, okay, so the mantra is type theory should eat itself. This is from, a somewhat famous paper of James Chapman. And I actually heard somebody say exactly eat itself yesterday. I think it was Ulrich yesterday. But more broadly, many of the talks, this week so far already have been about, consuming type theory by using type theory. And my slightly more refined mantra is a given type theory should eat itself, which is a little harder. And I'll explain, at least some way where I feel like this is an appropriate move. Okay, so you come up with a type theory, and traditionally, and I say traditionally so that Torsten won't immediately interrupt me. We have an operational semantics that we feel is true of the terms. We prove progress and preservation, we prove star normalization or some version of it, and then we get all the good properties from all these things, and we're happy, and then we send the type theory to the world to be beloved by all the people who learn it. This isn't that fun. I mean, it's a little fun, but it gets old. We'd sure like to be able to just come up with a type theory and then immediately have all these things. These days, people do NBE, which I think has kind of a slightly better story in terms of the machinery. It's a little bit less tedious to set up, but still a little tedious. Strong normalization, so where you actually have explicitly in front of you the reduction relation, does have a few advantages, and I think it's worth at least thinking about it a little bit. First of all, it's very explicit. It tells you exactly, how things compute. It can tell you how many times things compute and things like that. And strong normalization, says any reduction strategy works, right? So as you implement, you kind of have a pretty good idea of what your freedom of movement is. And okay, this is the real reason I care about this. There's still like one or two open conjectures. They're a little fiddly. The one I care about the most is this Benedict Hoover's conjecture, and I think Herman is in here somewhere, which basically says for a certain class of type systems, pure type systems, I'm not really going to explain what they are. If you're weakly normalizing, that is, all your terms, open and closed, have some path to a normal form, then every path leads to a normal form. And if you think about it for a minute, it seems pretty intuitive, but it's actually like surprisingly hard to prove. It's been open for at least 30 years, I think. Okay, so here's what I want to do. I want to take a theory T, and I want to prove strong normalization of T, and I want to do it in that theory itself, all right? And I want to follow the usual candidates proof, right? And the usual candidates proof is, Aaron talked about this yesterday, and we've had a couple other people talk about parametricity and logical relations. And so the candidates proof is a logical relations argument. You basically take a type, and you turn it into a very similar looking type, but it's actually a predicate over terms. And so, roughly a function from A to B satisfies the predicate if whenever it takes in an input that satisfies, the input predicate, well, applying it returns an output that satisfies the output predicate, right? So this is really kind of a messier version here on the right of what's on the left. But the complication of the candidates proof is that you also need to interpret these big pies in a slightly different way. And it's kind of annoying that there are two different interpretations of pies, and I'll talk more about that later. But the big pies, you need to instantiate them as, for all candidates, whatever that means, but at least they have to be predicates over terms. Well, T satisfies the body of that thing. That's the Girard trick. Okay, so why can't this work? The first reason is the Gödel incompleteness theorem. Basically, it tells you if you want to prove the consistency of a system that's strong enough, well, you surely can't do it in that system itself. And normalization implies consistency. And the second obstruction is type theories T may not even be able to say anything about syntax, right? It talks about internally, it talks about functions and elements, but it doesn't talk about terms itself. And even if it does talk about terms, it may not know how to do induction over those terms. So I'm basically going to explain how to address these three obstructions. Oh yeah, there's a fourth obstruction. T might not actually be normalizing. So that seems like a pretty big obstruction. Okay, so the first obstruction is a relatively simple trick, and perhaps it's even a swindle, which is based on this kind of folklore observation. I think it's due to hating, but maybe I'm just guessing or misremembering. Which is basically, HA is, a system of arithmetic. It can prove things. And whenever you can prove something in hating arithmetic, that means it has a realizer. And again, I'm not going to explain what this means, but that kind of, it's kind of like a logical relations argument. But HA can prove that thing is a realizer. So inside HA, you already have all the power to prove that thing. And why is that the case? Well, it's because you're looking at a concrete proof, right? And so you can have a meta argument that this is always true, but inside the theory, you only do it for a specific P as far as that theory is concerned. And definitely HA can't prove that every provable thing is realizable. That can't happen. You need to use a meta induction on this proof. Great. So let's do this. Basically, let's do a meta induction on a type derivation here, and the result of that meta induction is another term, which is an inhabitant of this thing that expresses that the syntax is normalizing. All right. You might notice that this gamma disappeared in between these two steps, and I'll come back to that. Okay. Obstruction 2. We can't even talk about syntax in a general, like, pure type system, for example. It just doesn't have a built-in notion of syntax. And the solution is just add it. Just add a new sort called syn, and then add an inhabitant of syn called term, and then inhabitants of terms that are just syntax for terms with, explicit substitutions and all the junk that you really want to have in terms. And then you need to add an elimination rule that allows you to quantify over things that have sort syn and arrive in some arbitrary sort from your original type theory. So here's where things get a little bit more messy. But that elimination will allow you to define a predicate called Sn, and then you're going to assume axioms basically about Sn, but all those axioms are going to be reasonable things that are actually true about strong normalizing terms. And in fact, it's going to be the inductive characterization of strongly normalizing terms that I learned from Andreas, who's sitting right there. He claims that it's folklore, but I don't know. So, okay. So, the beauty here is you add all this junk, and you even add maybe the explicit substitution conversion rules as new conversion rules. And the theorem we want here is that adding all this stuff is conservative in some sense. And in some sense, I mean, just preserves weak normalization. You add all this junk, you have new rules, you have new sorts, blah, 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 you have a new pi, but you don't break normalization because you've added relatively innocent things. Okay, so that's obstruction 2. And obstruction 3 is our inability to do induction within the system over terms or over, proofs of normalization. And it turns out that the usual Girard proof does have one of these inner inductions, right? It's outer induction on typing derivation. And then inside, you need an inner induction on like the well-foundedness of terms you've already proven are normalizing. So that's kind of not great. It turns out that the saturated set proofs, which is a mild variant, its setup is kind of nicer, and you don't need this inner induction, which is nice. But you do need this extra complication, which is every time you introduce, a predicate variable, which corresponds to a sort variable, you need to add these Girard-Tate conditions. And you don't really need to read them, but it basically says these are correct things that allow you to prove normalization. And you also need to add some computation rules that basically say, if you replace this x by Sn, this will cancel out with the existing things that exist for Sn. These new reductions are annoying, and the flake is a bit of my presentation, but I'm quite certain that this preserves the main theorem. And obstruction 4, the non-normalization. What's cool here, and I think this is the only really cool idea, what I'm telling you, it is that this translation still works for non-normalizing systems. You can still prove normalization for each individual term in a non-normalizing system. It's just that proof is just a bad proof. But that's okay. I mean, that's to be expected, right? You're in a bogus system and you get a bogus proof, and that's okay. And if you don't work in a non-normalizing system, if you work in a normalizing system, these proofs can be normalized. You can take their normal form. And it turns out that the normal form of such a proof of Sn, because we controlled the constructors of that Sn type very carefully, are real proofs. You can just read off the path to normalization off of that normal form of that proof. That's kind of cool. This implies the boundary Parvus conjecture by a relatively simple argument, which is you take a weakly normalizing pure type system, you build this extended system that knows how to reason about syntax. You do this translation, which works for every pure type system. You obtain these proofs of normalization, and then you find the weak normal form, you weakly normalize that term, you find a normal form for it. But that is a good proof of weak normalization. So now you know that this original T you started with was actually strongly normalizing. And you've used the system itself to produce that proof. All right, so confession time. I've carried this out for the STLC, it works. I carried it out on paper for system F. I'm confident that works. Those two systems are pretty boring. Here's a slightly less boring system. You take the STLC and you add a type with this equation. That does not terminate, but the proof still goes through. You can still build, for each term, a proof that it has a normal form or is strongly normalizing. I feel like this should work for the whole left side of the Barren cube, and indeed for all non-dependent pure type systems. Things get messier when you have dependencies. Unfortunately, these are already known cases for the conjecture, so this doesn't get me where I want to go. But it should be possible to get where I want to go because we know how to internalize logical relations for pure type systems. My inspiration for this whole shebang was this Bernardi and Lasson paper that was mentioned yesterday by Aaron. I don't know if he's in here. Okay, so let's do this. So this question has been open for a long time. Maybe we don't care as much anymore, but come on. I feel like we should be able to put it to rest, right? We've built up all this machinery. We have all this cleverness. And you know, another question is, this might work for pure type systems, but there's other systems, and this question still makes sense. And in particular, there are systems that normalize in the empty context, but don't normalize in a non-empty context. And this somehow story should break somewhere there, and I want to know exactly where. And I think these are interesting things to at least consider. And then finally, perhaps some of you have noticed that the flavor here feels like this thing called synthetic tape computability. It was introduced by John Sterling and elaborated on by others. And the question is, yeah, is this the same thing? I don't know. It'd be nice to figure that out. Unfortunately, you know, I don't quite understand what's going on there. All right. That's all.